Hello, everyone. Thanks for coming to this presentation. My name is Denis Magda. I'm a Vice President of Product Management and GridGain, and I'm Vice President of Apache Ignite Project Committee. And today I have a pleasure of co-presenting with Gil Ten, who is the CTO and founder of Azul Systems. Our talk for today will be about Java applications, Java middleware, and Java software stack. In particular, how that stack and applications can be used for so-called low latency use cases. Next, we are going to define those low latency use cases, describing the problems, requirements, and how they look like, work like. And afterwards, Gil will start with a deep dive introducing a software stack that combines a memory computing platform of GridGain with Azul Java Virtual Machine. And that software stack truly can compete with C++ stack for low latency use cases. But we just want to explain you how it works and how you need to be prepared for that. All right.
Well, with that, I'll sit here while
as long as unfortunately, we don't have any headsets, we are going to step up, step down whenever a speaker needs to be changed. But before we this is a technical conversation, but let's warm up a little bit and talk about a use case, a real life use case that happened in our history that can highlight the importance of latency. Specifically, how by reducing or optimizing latency of your important and crucial business operations, you can start using your existing resources much more efficiently and benefit from this later on. And I want to talk about Southwest Airlines. Let's jump back to the past, to 1970s. That time the airline business was highly regulated by the federal government. And the whole business was split between several major players. Southwest was a newcomer to the airlines area those days, and they struggled a lot. What they wanted to do is to provide a unique, exceptional customer service. They wanted to operate within Texas, but it took them many years to become profitable and to get a license, etc., etc. And they went through many legal battles. And after one legal battle, they had to sell one of their existing airplanes. So instead of 4 airplanes, they had only 3. And after that, the management had to sit down and think about the next steps. They had 3 choices. They either had to reduce a number of roads, but that would even more drain their pockets, damaging profits even further, or they might be able to sacrifice their customer service, but that was something that would make them more beneficial. They were not ready to sacrifice the customer service. Or they were able to come up with something else. And the something else was, they looked at the way how their whole business works, and they found one place where they were able to optimize their performance. They reduced a so-called turnover time of an airplane from 1 hour to 10 minutes. The turnover time is the time span when your plane that just got taxied to a gate gets prepared for a next flight. So you need to onboard your existing passengers, you need to board the other ones, you need to replace the luggage, you need to fill up your craft, etc., etc. And usually the average time was around 45 minutes and 1 hour. And their airline were able to reduce this time to 10 minutes on average. And by doing that, they were able to use limited resources, only 3 aircrafts instead of 4. They could preserve all the existing routes in Texas. They could stay in business, and even these days, we can have a pleasure flying with this airline across the country. What's important about this slide and about this use case, which is unrelated to the technical world, is that the latency, such as the turnover time, can truly optimize and sharpen your existing resources, your existing processes and business operations. And after that, you can take this model and soar your business further, scale it out. And now, if to talk about the present times, let's take several real examples where the low latency is crucial for some business applications. For instance, payments processing. Whenever we are coming to a store and like to finish a purchase, we are swiping on a card, but then in the background, we, as a customer, staying and waiting while a receipt will be printed out. But in the background, a lot of the operations happen. And some of the operations like fraud detection, authorization, verification, all of that have to be completed in a fraction of milliseconds. For instance, depending on the bank, depending on the service, some of the banks require this operation to be completed within 20 milliseconds. The other banks might require you to complete this operation in 200 milliseconds, but still, that's a quite small range for a transaction to be completed. When we are talking about electronic trading, that's even more severe and stricter use case. The guys who are working at New York State Exchange, they need to see all the fluctuations, changes of the stock prices, not just in milliseconds. They need to see this, their software, which means that the software, the IT infrastructure that powers New York Stock Exchange has to be able to process do a lot of the operations in a fraction of microseconds. It's even harder. And a good question, and the primary topic of this conversation is Java ready for such use cases? Can we use Java software stack to power credit card authorizations, do payments processing, or use Java for electronic trading? Generally speaking, if you look at Java stack first, you wouldn't see any kind of problems, pitfalls, or blockers. But there is one component that helps us a lot to develop Java software, focusing on the code, on the business logic. That component is garbage collector. And garbage collector is a bit unpredictable when we're talking about traditional garbage collectors. Because what can happen at any given point in time, a long garbage collection pulse or stop the work pulse can fire off and all your SLAs will be ruined. And basically this unpredictability sometimes excludes Java software stack from those use cases, when companies still prefer to continue using C++ software that doesn't have any garbage collection logic. But generally speaking, Java standard traditional Java virtual machines and SDKs, they are designed for generic use cases. It's fair to say that low latency use cases are specific one, right? And for specific use cases, we need to use a specific software. And today we are going to explore how to use Azul Zing, Java virtual machine that can avoid garbage collection pauses for your Java processes. And then once you optimize your Java heap utilization processing, eliminating pauses or minimizing them tremendously, after that you can scale out this approach, this solution, to terabytes or petabytes of data with the help of a memory computing platform of GridGain or Apache Ignite. So having said that, let's talk about Azul first. And Gil, please introduce us to this wonderful technology.
Thank you, Dennis. So hi, everyone. I'm Gil. I'm the CTO at Azul Systems, and we're going to talk about Zing, which is the lower part of this stack that we just discussed. Azul Zing could simply be thought about as Java, everything you're used to in Java, except for the bad stuff. So it's Java without the pauses, but with all the other good things. And it just drops in and runs pretty much any Java application you have today. As a quick overview of Zing, simple picture is to say this. If your application looks like the thing on the left and has glitches, and you want it to look more like the thing on the right, that's what Zing does. What application it is doesn't actually matter. If it has glitches like the ones on the left, we know what the culprit is usually. And it's the one that Zing solves. So Zing is a JDK. It's a JVM for x86 Linux machines. It basically focused not just on speed. It is fast, but it's focused on speed being consistent, on being always fast, consistently fast. It improves application metrics, so whether it's speed itself, consistency, number of nines, outliers, etc., the ability to carry workloads within SLAs on a given number of systems, so it's capacity as well. So you can carry more within the same resources, cloud resources or your own resources. And it also makes developers a lot more productive because it allows them to avoid all the time they sink into working around the problem that shouldn't exist to begin with and focus on the actual business value of whatever it is they do. And that tends to make their managers happier too. Zing focuses on continuously responsive execution. As I said, the consistency is key here. And it does that by practically eliminating garbage collection as a concern at the enterprise application level. When we look at true low latency at the microsecond levels and such, you will still see glitches, but the glitches you see from Zing are in the same order of magnitude as the operating system or below. So usually the JVM is no longer the culprit or the main culprit in whatever jitters or hiccups you have. It also reduces other things about speed, like the behavior during deployment and rollout of new software. Zing has an extremely wide operating range, so we're probably pretty well known for being really good at really low latencies or really good at humongous heaps, but we're also really good all the way in between. So everything from a gigabyte to terabytes, everything from low latency to batch streaming, and everything in the middle like human response times, all of those are affected in a similar way. The consistency is there. The areas where we shine is pretty much anywhere responsiveness matters. Human response times, you'll see Zing in many, many applications you deal with daily, including online booking and payment processing and other things like that, but also just marketing systems. A lot of machine-to-machine stuff, whether it's microservices, service buses, message buses, any kind of communication, which is most communication today. And then you get into the low latency or latency sensitive things. I like to look at this scale because it's shifted a lot. I love this story about Southwest in 1970. That was low latency. 10 minutes was low latency. I think we shave an order of magnitude or two, a couple zeros out of what we think low latency is, and in almost 50 years since then, we've shaved probably about 8 zeros off of that time. So now low latency is 20 microseconds. 20 milliseconds is, okay, that's latency sensitive. You know, people at the other end don't like it when their credit card thing is waiting too long, kind of stuff. And then we have a lot of in-memory analytics use cases where I think in-memory computing is the interesting intersection of large in-memory analytics or processing with latency-sensitive operations. Here are a bunch of infrastructure pieces of software that just get better when you run them on Zing. All of these happen to be in Java. They happen to run on JVMs because it was very productive and scale to build them in that. And as a result, they're susceptible to the weaknesses of a JVM. They're also susceptible to improvements with Zing because we take away those weaknesses. So every one of these things, whether it's a search engine, a database engine, a message bus, or an in-memory controlling platform, or just analytics processing, gets better if the JVM underneath is replaced. If you want to look at it from your application's point of view, whether you build API gateways or back-end systems or front-end systems or in-memory analytics, those are all pieces of logic you build that could get better. And if we look at the features that make it get better, there are three main areas in Zing that do that. The first one is the garbage collector. We call a garbage collector C4. Stands for the continuously concurrent compacting collector. That's 4 C's. It also explodes memory, so that's why it's a C4 collector. We have a compiler, which is basically about speed. It's a faster code. And we have a technology we call Ready Now that improves the behavior of speed as you start. So it gets faster. I'm going to look at the shape of speed a little bit to explain where there's map. In general, when you look at speed, everybody wants it to be fast, right? You want good speed, but what is speed and when do you need it? And when do you need to be fast? So are you fast all the time, or are you fast only when you're not delivering software? What if you deploy software 20 times a day? Are you fast even then? Or are you fast all the time, or just when there's not a lot of load and Can you survive a Black Friday or a marketing event or a news event? Are you fast when the market opens, when things actually matter and volatility is high? And are you reliably fast, or if you run fast for a while, this happens? Right? These are all questions about speed that go beyond what the number is. It's the behavior of speed. And we would like speed to behave like this. That's the ideal speed. You'll never see anything that behaves like this with speed. But we all like to model it that way. Speed in Java environments behaves according to this shape, roughly. This is an actual behavior of speed over time. And this comes out of multiple different parts that play together. The first one is that when you run in Java, code evolves. You start with slow interpreted code when you just start running, and then it gets faster and faster because the JVM pays attention to it and optimizes it, and eventually all your code you're running is nice and blue and fast. But everything started slow. And to get to the fast, you have to hurt a lot of things. A lot of things need to be slow before they get to be faster. That happens every time you start a new instance. If you look at what that does to response time, it starts slow and gets faster. Now these red things are the other things that are not the evolution, but the unfortunate outcomes of glitches and garbage collection pauses and things like that. If we look, this is response time. If we look at this as speed, it's 1 over x. It's this shape. You start slow, you go faster and faster and faster, but even when you reach that plateau of good speed, you go to 0 speed for milliseconds, tens of milliseconds, maybe seconds, and then you come back to full speed. Java is really, really fast between terrible, terrible slowdowns. Now the way Zing maps onto this is we increase speed simply by making code faster. That's easy to understand. Our Falcon JIT makes things faster. We improve the shape of speed with our Ready Now technology that brings the code to speed faster. You don't have to wait as long, you don't have to hurt as many operations before you get to speed. But most importantly for in-memory computing, we take away the glitches. We eliminate those downsides. And the way that ends up turning out is what we're going to be looking at here. Looking at the benefits to actual operations, garbage collection, who here has dealt with garbage collection problems? Yeah, okay, so we're in the right room. And how many of you have had to deal with tuning garbage collectors? Okay, so you might have seen some of these flags. Or maybe some of these flags. And some of you might actually know why this number needs to be that number and not this number. Because it's a Tuesday and not a Thursday, maybe. Or maybe because the application load changes, or maybe it's a different application. But you need to find the right number for every one of these. And there is no right number. There's the right number for you today. Things are very sensitive. So those of you who have tuned it know the enjoyment that you get from doing it. Sometimes it is enjoyable, but and you might know about a few more flags, like some of these. One of the big things that happens from eliminating the GC problem is eliminating the need to play with all these things. There's these many, many different sensitive things, all of which have a right value you need to find is a big problem. The modern way GC tuning looks today, 2019, we have Zing, it's readily available, and other collectors are being developed, which in 4 or 5 years will probably get to the same step, is you just give it a big heap. Just do that, it's gonna work. Big is probably whatever is bigger than what you think. But that's a waste, right? We don't want to spend all that heap. So squeeze it down, cut it in half. Is it still good? Yeah, cut it in half, cut it in half. Do that until it breaks. Now you found the setting you don't want to have, then double it and go home, you're done tuning. That is what GC tuning looks like with Zing. It's finding the amount of memory you actually need to run your application so it no longer pauses, because it won't pause if you give it the right amount of memory. When I say it won't pause, I need to be accurate. Zing does have little glitches and pauses, exactly 4 flip pauses per cycle, but they're in the sub-millisecond level. And to show you an actual thing, this is a Cassandra workload at heavy, full load, running 90,000 operations per second on an actual server. That is the 1 millisecond pause line. So we do pause, just at numbers that only traders care about. Okay. So let's bring this into the real world context here. This was the bottom part of the stack. I talked about how we have a JVM that makes things better. Let's put it together with things that use it. And what we are going to show you together here is numbers from a real world use case. It's a payment processing system with credit cards. It's running GridGain as an in-memory computing platform on top of Zing. And the overall setup used to collect the benchmark results you'll see here that reflect the same is an AWS setup. So this is in a public cloud. It's, it's susceptible to whatever glitches AWS does to you. But remember, GC is much worse than that. We're going to show you that now. We're running on 3 AWS nodes, 72 cores, 600 gigabytes of RAM, nice setup. And the tested scenarios are both Zing and regular OpenJDK hotspot with G1 collector. That's the latest good collector there. And we compared 3 scenarios. One of them is a full 100% in RAM, in-memory computing setup. The other one is the same setup, but it's not just in RAM, it's also persisted. So everything is in memory, but also persisted. And then we have a scenario where we have the persistent stuff there, and only about 30% of that is in RAM, so that you can actually have larger data sets than your in-memory stuff can handle and still maintain speed. We look at measurements in all 3 scenarios. The actual workload does 20 accesses per operation, per transaction. So whether if it's reads, it's 20 different records being reads. If it's updates, 20 different records being updated. And the workload parameters are these. For transactional reads, it's doing 1,000 operations per second. Each one of those is 20 records. And the required latency on those reads is there. It's 15 millisecond for the 4 nines. Now that might seem like a large number, but it means that, every 10 seconds you're allowed to have one thing that goes above 50 milliseconds. And that's still a lot of things that will go above 15 milliseconds. The other part of the workload is a transactional update workload, same number of records, running at 2,000 updates a second. And the SLA there is more lax, because these are just the updates. It's 50 milliseconds for the 4 nines. Now, the actual collection metrics were done both at the low level, looking at the system for glitches and stuff, but also at the actual application level to look at the measurement experienced. And we're looking at a 2-hour total run. 2-hour total run gives you enough time to see actual system behavior. Usually if you run 5 minutes, 20 minutes, your tuning most likely just moved the problem to minute 21. So you want a long enough run to see what actually happens. You're going to see some of the results that show that if you don't wait long enough, you haven't measured enough yet. So here are results. These are transactional reads. What you see on the left is the G1, and what you see on the right is always C4. Now, okay, the shapes look a little different, and you can compare the two, but they might not look that different until you actually look at the y-axis scale. If we actually scale this to the same y-axis, this is what it looks like. And the reason this is important is right there is the SLA line. Right? So if you cross that red line, you're broken. Zing is not broken. OpenJDK at this load is broken for this workload, for that specific SLA. If we look at updates, we see a similar thing. So remember I told you, got to run long enough to see the bad stuff? Well, here's bad stuff that happens only if you run long enough, right? So the maximums later in the run started getting worse. And again, this is not to scale. If you draw them to scale, they look like this, and there's the SLA line again. Passes with Zing, doesn't pass without. These are transactional reads with persistence. So far we're looking at in-memory purely, no persistent at all. This is with persistence, so everything's in RAM. You get the speed of doing that, but you also get the full persistence benefit. Similar comparisons. And to scale looks like this. The thing to highlight here is once you add more complicated things like persistent into the workload, the gaps go much, much wider. The actual work gets bigger. What you actually need to do to perform is there. The number of nines, at 4 nines, the actual latency went through the roof on the OpenJDK case, but Zing maintains similar results to what was there before you went to persistence. And that's because the garbage collector is actually able to handle this additional churn of objects coming in and out without the pauses. Similarly, updates with persistence. This is starting to get boring with all this rescaling, right? But here's the side-by-side same scale. You can see the dramatic difference in the behavior. And again, the SLA is right there. So what you're seeing here is basically the actual impact of just replacing the JVM under the hood with one that actually works well for latency-sensitive environments, for in-memory environments, and seeing the benefit that comes from that. And with that, I'm going to hand it back Dennis to finish looking at the rest of the stack.
Thanks, Gil. So folks, right now let's also recall that example of Southwest Airlines. So what the company did, they found a way how to optimize an inefficient business step, the turnover time. And here is this benchmark shows that you have your cluster of machines, or probably one machine. You certainly know that there is one possible component that will cause and trigger all of those instabilities. Turns out that even with Java stack, you're pretty comfortable with low latency use cases, but you need to use a special virtual machine that has a C4 garbage collector. Now let's talk about the scalability. Let me also explain you the details of this architecture. For that benchmark, we were using 3 GridGain nodes distributed and located on AWS. On each node, we were studying one JVM process, GridGain server node, and that every process was powered by Azul Zing virtual machine. And what's interesting here when it comes to the memory usage, GridGain's memory-centric architecture utilizes RAM a little bit differently from other memory computing platforms. We do not use Java heap to store your actual data, your objects, your records, or your indexes. Everything that you put into the cluster when you're doing the initial load, etc., it will be stored in a heap region. Whenever you start that JVM process over GridGain server node, the process will go to the operating system and will tell, all right, give me that much RAM. I will use that RAM as a storage. So, and each process will manage this memory, allocation, deallocation, cleaning, defragmentation, etc. But still, we are Java middleware. We use Java heap sometimes aggressively, especially when it comes to the low latency use cases. With this benchmark, we could see that, unfortunately, G1 garbage collector started choking when we put that excessive load transactions and reads in runtime. But with Azul Zing, everything went fine. And actually, that benchmark is a pretty interesting story. That's something that's a real benchmark that is used by one well-known bank to assess and verify certain technologies for credit card authorization. And how do we use Java heap? Why like the difference is so dramatic? Whenever, let's say that you started your cluster, you preloaded initial data like 200 gigabytes for that performance benchmark. But after that, you start using that cluster. You run transactions, you will read records, you will update records, and whenever you are reading records, for instance, running SQL queries or key value operations, GridGain will go to that off-heap storage. It will be preparing a final result set for your operations, and everything, all the temporary objects, result sets, will be stored in Java heap. And whenever you put that excessive load, like 2,000 transactions or reads, you are just allocating and using much more Java heap. So the garbage generation rate will be much larger, and which will kick off more frequent garbage collection pauses. At the same time, guys, let's be serious. RAM and memory computing is all great, but when you are using any in-memory computing technology, you cannot sacrifice data loss or inconsistency. For that payment benchmark, persistence was not an exception. Yes, I'm ready to take your wonderful, shiny, bright in-memory computing platform, but look, what do I do if my data center loses power, if everything goes down? I don't want to lose the data. Or probably sometimes, at some point in time, I'm going to scale to 5 terabytes of data or to 10 terabytes of data. And at that time, I might not have enough RAM capacity. I want to go to disk, I want to read from disk. So are you able to do that? With GridGain's unique memory-centric architecture is designed and optimized for RAM as your storage, or for Intel Optane as your storage. But when it comes to disk, you also can easily and freely use it as your storage tier. For instance, you are not required an entire data set in RAM with GridGain. It's up to you. Like with these benchmarks, as Gil showed, we cached 100% of data in RAM, but also you can cache only 50, 20, 10, 5, whatever you need. Depends on your capacity. It depends on your trade-off. How much speed you want and how much resources do you have. Also, it means that if we cache, let's say, 30% of data in RAM, somehow we need to be able to go to disk in runtime. And GridGain's persistence is active and transactional, meaning that it's not just a silly backup storage that you would use on cluster restarts. That's your normal disk tier. If any piece of data is missing in RAM, GridGain process will go to disk and retrieve all the data needed from there for you. You're not doing anything. You just enable a special property in your configuration saying that, all right, for this GridGain machine, I need that much RAM for storage, that much heap for Azul Zing, and that much disk for persistence. That's it. And what's good about this? If to recall those benchmarks, we saw that with Azul Zing, we still have a lot of room, probably for extra workload. We didn't meet, we were quite far from, crossing all of those SLAs, which for us means that we can put even larger load with Azul Zing, processing even many more operations and transactions, or probably we can look at how we can reduce our infrastructure cost. And this benchmark, for instance, we decided to take the same 3 nodes cluster, but instead of 200 gigabytes, we preloaded 600 gigabytes. And also, now we store only 30% of data in memory, which means that in most of the times, whenever you do transactional reads, the cluster nodes will go to disk and will read all the data from disk. And that's how the benchmark looks like. If, again, we equalize the scale, this is how it looks in real. What's about transactional reads with, and that's the SLA, that's the cross mark. You can see that even for 2.9 or like even for 3.9 SLAs, unfortunately G1 was not able to meet the SLA requirements. But with Azul Zing, we are still pretty far around that point, but we are not crossing it. When it comes to the updates, the story looks pretty identical to the previous benchmark when we cached 100% in memory. But still, the equalized benchmark, and you can see that, unfortunately, with a traditional Java virtual machine, we fail all the imaginable and possible SLAs, while with Zing, we still feel comfortable. So what this benchmark and the whole story can teach us about? The primary question we wanted to ask when we started collaboration with Azul is to see if we can use Java stack for low latency scenarios. Because at some point, at one time, like in the past, what happened? GridGain, like we were working with one of the big opportunities, and unfortunately, due to the traditional garbage collectors, we lost that opportunity to a C++ stack, not to a Java stack. Our platform is insanely fast. It's scalable. But when you get into the microseconds or milliseconds, you are competing with C++. And right now, yes, we have this stack. And this stack, the primary components, you have Azul Zing, and it's C4 garbage collector that can make things pauseless, even though like there are some of the pauses that happen at the microseconds tiny range that, as Gil said, probably will be visible to the traders, but we do not notice them. When it comes to the horizontal solution, once you optimize your workloads for, let's say, 1 node or 2 nodes cluster, then you're ready to go. Like with Southwest Airlines. They optimized that process as good as they could, and after that, what they needed to do is like, buy more airplanes, to do those routes and accomplish the business stuff more efficiently. And with GridGain, the story is the same. As soon as you are ready to scale to terabytes of data or petabytes of data, you just do this easily and step by step. Just add 1 more machine to the cluster, load more data, the workload will be distributed, and Zing will ensure that you still meet all the latencies. And what's good about the memory architecture of GridGain is that you have a choice. You are not required to cache an entire data set in RAM. It's up to you. If you have resources, for now, cache everything, because you will get the best speed and the fastest kind of response time possible. If by some reason you are able to cache only 80%, 30%, whatever, it's up to you. You have a choice. You have all the parameters. So having said that, we have still plenty of time for questions and answers, so Neil, please come on stage. Any questions?
So how do you avoid large scans in memory? So the garbage collector has to find pages too big. So it has to go scan and find pages that are not dirty, that are not locked, and then puts in a list that you will delete later. How do you avoid a large scan? Do you feed the list preemptively, or?
So the key thing to the Zing Z4 collector is it's concurrent. We don't avoid doing the work, we just do the work without stopping anything. And none of you are running on 1-core machines, I hope. So concurrent is truly concurrent. We've got multiple CPUs. Even on 1-core machines, we could probably interleave at the 10 millisecond level, but it's just truly concurrent. There is actually a full peer review academic paper describing the C4 garbage collection algorithm from ISMM 2011. We've been shipping this collector since before then even. And the fundamental way you can think about it is the collector has a pretty simple job. Once you fix concurrency, and it's pretty simple, it, in the background, needs to go and find all the stuff that is alive. It's not pages, it's objects, but it will follow and find everything it can reach from roots. Make sure it knows it's alive. It, by doing that, detects everything that's not alive. If it didn't reach it, it's dead. It then needs to reclaim the dead space, and the simplest way to reclaim dead space is to take all the live stuff and move it somewhere else. It's called evacuation. And we do that in what we call a relocation step. Once we've identified the live stuff, we go and take all the stuff that's alive and we move it somewhere else. By moving it somewhere else, we get these nice contiguous empty areas. However, when you move something somewhere else, there's a billion things pointing to it where it was, and we need to do this fix-up or remap of references so they point to the right place. Any collector that moves objects in memory has to do all 3 of the things that I just described. Every collector in Java moves objects in memory. So all 3 of the things I just described happen to every garbage collector out there. The interesting challenges are, how do you move an object from one place to another and let your application run without first having to fix all the pointers in the world before I let you run? The big stop the world pauses come from either finding all the live objects or, more importantly, when I move stuff, can't let you run and use bad pointers, so I have to fix them before I let you run. That's where that G1 pause comes from. It's an incremental pause where it moves a little and then it fixes everything it can, then it lets you run again. It's better than the previous ones, but it's still in the hundreds of milliseconds. With Zing, we can move the objects and we don't have to fix the pointers until we want to, because the concurrency operation takes care of you observing a pointer that needs to be fixed and getting it fixed right there without waiting for anybody in a sub-microsecond operation. By doing that, we can keep everything concurrent. We can push the fix up to later. We even make it twice as efficient than a stop the world collector would be, because we can do the fix up of pointers during the mark of the next cycle. We do one pass to do both. We don't visit things twice. Everything gets better and happier. It's all about enabling the concurrency. And the paper details the full algorithm for how we do that.
So basically it's a trade-off between using more CPU. So the trade-off is...
No, we use less CPU and we are concurrent. We're twice as efficient as a stop-the-world collector and we are concurrent. I know that sounds like a pipe dream, but numbers.
No,
Yeah.
I trust that.
I think there's another question behind you there.
So all that wonderful three-step magic that you do there, you gave a simple example of how to tune the GC memory.
Mhm.
It implies that there's a cost for extra memory. Is there in fact a factor, like a 50% more to get this working, to have the remapping and parallelization all working?
So the tool of using extra memory to affect efficiency is there for all collectors. The reason most people don't use it is because extra memory means larger pauses. So people usually limit their size of heap by the worst pause they can stomach. When the pauses go away, that math changes, right? Then use memory for what you want to use memory for. There is specific math to what it takes to stay concurrent. Because obviously, if you allocated a terabyte per second and we couldn't free up memory that fast, you wouldn't be concurrent. So in order to keep up, we have our work to do, which is basically figure out where everything is and compact it and generate empty memory at a rate per second as a result. And you're out there allocating at that rate. As long as we can keep up, we're good. That heap knob that I talked about, it's a very simple tuning knob because the algorithms we chose for the collector have this really cool quality. If for every doubling of empty memory, the algorithm uses half the CPU. So think of it this way: if you had a gigabyte heap and a byte empty in it, it wouldn't matter what algorithm you use. Every time I need to give you another byte, I have to find it in a gigabyte. That's a lot of work. If I have infinite memory, I never have to garbage collect. Doesn't matter what the garbage collection algorithm is, it's very efficient, right? Somewhere between that, I've got 1 byte empty and infinite memory, there's a 1 over x line that exists as long as your algorithms are chosen right for only growing with the live matter without the empty heap. Never visiting anything dead, only visiting things that are alive. And we carefully designed it that way. As a result, suppose you find that you spend 15 or 20% of your time in GC cycles, and you don't like that. You don't want to waste that CPU. Double the empty memory, that number will come down in half. Double it again, it'll come down in half. Do that as long as you want to cut the CPU down. You can work the other way around too. You think this is waste of memory, shrink it down, you'll use more CPU. It's a direct trade-off that's under your control. It's perfectly smooth because there are no pauses. So now the tool is yours. Most of our customers tend to choose I would say in enterprise transactional applications, it's usually, they try to keep the collector below 5 to 10% wall clock utilization. They want it idle 90% of the time, makes them feel good, there's headroom. In low latency applications, they'll typically go down to 1 or 2% because, like the actual traders, they care about that 200 microsecond blip. So they want even that to be rare, so they'll throw memory at it. But most people run with I'd say above 5 or 10 gigabytes. We're looking at hotspot similar heap sizes. We don't actually need more memory, we're just concurrent in it. But you can add more memory and be more efficient. You can add more memory and triple the load that your node can take. One of the things we hadn't actually mentioned here is we looked at this and said, okay, that's the workload, Zing passes, hotspot doesn't. And then we said, well, is there a load under which hotspot does pass? Maybe if we went slower, We tried, we went 10x slower, it still didn't pass. It had fewer glitches that were further apart, but there was still a minute or two during the 2 hours where it just didn't do it right. There's probably a level where it would have passed. When we look at more like typical transactional operations that are not as SLA sensitive, say on AWS, we typically see Zing carry 2x, 3x the same transaction workload on a node before it cracks under load. At some point, we won't be able to keep up either, the CPU is full. But the reason for cracking with Zing is the machine is full. Where the reason for cracking with other JVMs is the GC pauses are getting too bad. So I've been hogging the mic. Maybe you guys have some questions for the GridGain side of things too.
No, this crowd
Yeah.
is experienced in our GridGain, etc.
Okay.
Question ladies. So how does it actually relate to applications? You install Zing, then on top of it you install GridGain, right? Then you have pretty rich environment as far as the amount of nodes in the GridGain goes. How does the Zoom finds basically the weaknesses where it needs to cleanly? You have, for example, you have many nodes. How does it find the weakness? How does it watch an environment, so to speak? GridGain environment.
So here is GridGain again. That's your, think of it as a distributed storage and computing platforms. Basically, each GridGain process, when we're talking about a cluster, that's a cluster of GridGain processes interconnected with each other. So and for us, for an application layer, they're just single entry point. For you as an application developer, there will be no any difference by default, whether you are working with a relational database that has one connection open, or you just can start an application that connects to a GridGain cluster. You're not usually working with each individual node, you're working with the cluster. But each node is a GVM process. Just that when we store the data within that space allocated from the operating system, we steal a Java application, if to be simple. And as Java application, whenever any of these nodes receives a request from your application connected to the cluster, it needs to go to the memory space where the data is located. We need to run some queries, operations, prepare result set, and all the temporary objects that are generated during your queries serving and processing will be utilizing Java heap. Java heap is used like by any other application in Java. We generate some garbage. All those objects will be placed into Java heap, and then at some point of time, garbage collector has to remove it. And here is in this configuration, when we are saying GridGain plus Azul Zing, it means that whenever we were starting a GridGain cluster node, we were using Zing virtual machine. Whenever we were running G1 benchmarks, all those charts, instead of Zing, we had identical configuration, but instead of Zing, we were using an OpenGDK, one of the versions. Tuning it hard.
I think, so to clarify the relationship there, Zing is just a JDK, just like any other JDK you run. You install it the same way. You choose which Java you're running on, what GridGain is running in, or your own application, simply by choosing the Java home directory. And when you point it to Zing, you're running on Zing. When you point it to OpenGDK 11, you're running on that. OpenGDK 8, you're running on that. Just like versions of Java. It's just yet another one you put on your machine. If you run on that one, it doesn't pause. It doesn't look for where to help. If you run on it, that one's good, right? So in this cluster, all of those nodes were running on Zing JVMs. And that's what made them smooth and not take those hiccups.
So what tunings are involved in Zing?
What tunings are involved? Well, I showed you what happens to all the flags, right? Now, I actually, as a CTO, I have this constant fight with our own technical people because people love to look under the hood at all the flags, and we have flags, and you can change things, and you could probably get 0.5% better if you did. But usually we try to make the point of you don't need to. The big tuning knob is the heap size. All those other things were there to delay pauses. The pauses are gone. You don't have to do any of those. Now, yeah, there are places where you could, in some places people play with the number of threads the garbage collector has because the default isn't perfect. They could get maybe a little less CPU, a little more CPU, a little more time, a little faster allocation before they crack if they just tweaked it a little bit. But you're talking, those are tunings you do when you've reached the edge and you're trying to figure out how to push the edge another %. With Zing, you usually figure out where the edge is and you just stay far, far away from it. And it doesn't really matter how far. You know, you just, like I said, find out the heap size that cracks, double it. Just double that, stop. You know, don't figure out how to run at 5.07 gigabytes because that's the most stuff you can have with the biggest pause you can handle. There's no pause that's going to happen. So just don't waste memory, but don't be stingy with it so you might be sensitive, right? You really don't know what the real world's going to throw at you. Buy that headroom, right? And the differences between optimizing for a peak where you've gotten all the right values to keep it there, and finding the edge of a plateau, finding the cliff, and just staying away from the cliff. Any of the numbers on the other side are good. There's no one right number. Just don't do the bad ones, right? And that affects generally the tuning for throughput and memory and those kind of things. We take the same approach with our JIT compilers. Yeah, there are lots of flags that people know about and we experiment with, but we don't want people to have to use flags. It should just work. It should have a very wide, smooth operating range, and only the people that are trying to get the last 1% need flags.
All right, I
Yeah.
think we need to take one last question because we're already running out of time. Let's do it quick and then
You want to pick who won?
Yeah, fine.
I guess, yeah.
So our current situation is we're throwing volume, not Azul obviously, we're throwing volume at it and we're doing full table scans, and that is creating too much garbage for our garbage collector. We're actively tuning, but you mentioned headroom. How would it be different if we had Azul running, since it's a different garbage collection, would it be better able to handle all that garbage you're creating, or would it
My expectation would be exactly what you said. Out of the box, it'll be able to handle it. The only question you'll be left with is how much heap. We're 99% good at doing that. That's why I'm so confident. I really don't need to know much about it other than you said that garbage is causing problems. The practical thing there will be basically the collector's going to do the same work but won't pause on you, right? So the thing you're trying to get away with will go away, will go away. The key question I ask is, you know about this, you've played with it, you figured out that the tables are causing GC pressure. Think of the time you spent. Think of the time your people have spent looking at this. If that was running on Zing, we wouldn't be having this conversation and you wouldn't even know about it, right? And that's the value. People don't even need to know this stuff anymore. It's not a GC tuning mechanism, it's a forget about GC mechanism. And if you're interested in GC, we can have a really deep conversation, but maybe you're interested in other things instead.
Yeah, for us, it's a risk mitigation right now. If we just spend time SQL tuning and not doing any full table scans, or crashing out before Q1,
Yeah.
Yeah, so actually that's
mitigate the risk, then
many of us. Yeah, many of us were able to attend Craig's talk yesterday. So they're using in production GridGain cluster, but their workload is different. They're hitting and issuing a lot of SQL queries of various complexity, joins, like grouping, etc., etc. And at some point of times, the heap, etc., got overutilized, and periodically it led to some out-of-memory poses. But here is another problem. Like, I think that with standard traditional garbage collectors, you still kind of you can hit a ceiling with the maximum heap possible, because otherwise your garbage collection poses can last for hundreds, like dozens of seconds. And that's why you always kind of cannot cross some beyond, like some point. With Zing, as far as I believe, you can truly create a much larger heaps.
Yeah, so it is important to note, if you do fill the heap up completely, we will crack just like everybody else, but only then. I'm actually dealing with a log from a customer who's complaining that 87% life set utilization, the CPU is too high. Not that it's pausing, it's just he doesn't like how much the CPU is running. The answer to that is give it more heat. And the good news is Zing will take any amount of memory you can put a machine against. So our maximum heap size right now is 8 terabytes. We can't do more than that right now. Next year we'll do more. But most of our customers never reach any of that. Usually it's in the gigabytes, tens of gigabytes. We have people in the hundreds of gigabytes. We have data grade operations that are running with 600 gigabyte cache instances for credit card payment processing and doing good risk computations in that. It works just fine. But if you did fill that up with 500 gigabytes of live stuff and cracked it a lot, we might need another couple hundred gigabytes of empty space to keep up. Memory is your friend then, and memory is much cheaper than CPU. So you can usually just get the right size machine, especially if you have the freedom of working in an in-house cloud or a public cloud of some sort, and just any number you need is there.
All right, let's do the following. I see that there are still some hands in the air. You can come over to us, but we will let the other guys go.
Yeah, let's say it's over, but not over. Yeah. Okay. Thanks. Thanks, everyone.